Hello. If you missed class today, you missed the doozy. We talked about the quantitative relationships between Boyle's law, Avogadro's law, Gay-Lussac's law, and Charles's law. Basically what we did was we said, okay, if the temperature is going to increase by X amount, the pressure is going to whatever. So we were able to first, we used our first, this is the first class period that we've actually made quantitative predictions about what would happen to the pressure, or the volume, or the temperature, or whatever. So to give you a little background, this is a summary of what we did. These top three were things we'd already talked about. This one is a new one that I threw in today. But basically what we did is we said pressure and volume, when we talked about Boyle's law, pressure and volume are inversely proportional. The way I know that is if I take a balloon and I squeeze it, decrease the volume, that's going to build up the pressure inside of the balloon, which is going to want to cause the balloon to pop. So therefore, that is what we call inversely proportional, which means if I double the pressure, I would halve the volume. If I multiplied the pressure by 100, I would divide the volume by 100. That's all that means. Avogadro's law is the law we looked at next, which looked at the relationship between pressure and the number of particles. And so that we said that those were directly proportional. So I can think about that in my head because I know if I have a balloon and I continue to blow more particles into that balloon, the pressure is going to be building up, right? So therefore these guys are directly proportional, which means if I double the number of particles, I double my pressure. Gay-Lussac's law says, it talks about the relationship between pressure and temperature. So I can think about that because I know that if I heat something up, the particles are going to start to move faster. If the particles start to move faster, they're going to be colliding more. If they're going to be colliding more, that means a higher pressure. If this goes up, that goes up. However, they're only directly proportional if I'm talking about that in the Kelvin scale. Okay? In the Kelvin scale only. And then today, Charles's law, which looks at the relationship between volume and temperature. And I can visually think about that. If I increase my temperature, that means the particles are going to expand. This is called thermal expansion. The volume is also going to expand. So therefore, if this goes up, that goes up. They're directly proportional. So if I double the temperature in Kelvin, I'm going to double my volume. All that being said, now we can use this information to now solve problems like this. Where I have so it says a gas has a pressure of 410 millimeters of mercury at a temperature of 25 degrees Celsius. What would happen to the pressure? What would the pressure change to if the temperature increased to 35 degrees? So the way I'll introduce this, we're going to use this thing called an Eiff table to solve problems like this. But the way I'm going to introduce this is by simply drawing a picture. And so I know I have a gas, okay? And let's say I have my gas, it's defined at a certain volume, and I've got particles in there. And those particles are moving, and so however your class has defined motion, I'm going to do this with the blue sheets. So I've got them moving, okay? Then I know that so I know some things about these particles. Like I know that the pressure, like in the first sentence, it tells me the pressure is equal to 410 millimeters of mercury. And then I know that the temperature is equal to 25 degrees Celsius. So then I know I'm creating a change. So basically what I'm doing is I'm heating these particles up. The volume stays the same. My number of particles stay the same, but I'm heating them up, so therefore I'm showing faster particles over here. Because my temperature increased to 35 degrees Celsius. What's that going to do to the pressure? That's the question. I want an exact number for the pressure. So the way we're going to solve this is by using what's called an Eiff table. So if I call this initial, because it's initially what the gas was like, and this final because this is what the gas turned out to be, gas conditions turned out to be, then I'm just going to come over here and I'm going to create my table. Call it initial, final, and E stands for effect. So this is an Eiff table because I have I, F, and E. I'm going to create the table. These are the rows of this table. The columns or whatever variable could be affected about a gas. Like for instance, I can manipulate pressure. I can manipulate volume. I can manipulate the number of particles, and I can manipulate temperature. Okay, so now what I'm going to do is I'm going to say, okay, initially, do I know the pressure, volume, number of particles, or the temperature? The answer is yes. I've even labeled them over here. Initially, before I do anything to that gas, I know it has a pressure of 410 millimeters of mercury. So I'm just going to write that in that table under initial and pressure. Well, I also know that the initial temperature is 25 degrees Celsius. I'm just going to write 25 degrees there. The final pressure I don't know, so I put a question mark there, but I do know the final temperature, that's 35 degrees. Now notice how it doesn't say anything about volume and number of particles. What that means is I tell these guys constant, that's constant. Which means I do not have to worry about them, so I just put an X in there because I don't have to worry about it. So now, the question is, how do I solve this? Well, the question is, what is the relationship between pressure and temperature? Pressure and temperature. Well, let's get this board over here. What is that relationship between pressure and temperature? Oh, there it is, Diluc-Sachs law. Pressure and temperature are directly proportional, but it's only directly proportional if it's in a Kelvin temperature. So when I take this guy back here, I need to make sure whenever I'm dealing with the ICE table, temperature is always in Kelvin, every single time. So right now I've got them in Celsius. I need to quickly change them to Kelvin. The way that I do that is by take my Celsius degree and I just simply add 273 to that number. That should give me my Kelvin temperature. Just like so. So then 25 plus 273, that comes out to be 298 Kelvin. 35 plus 273 is 308 Kelvin. So now, I have changed my temperature to Kelvin. And I've got this whole table filled out except for this effect row. The effect just simply means this. What's happening to my temperature? Well, I'm going from 298 to 308. That means I'm increasing my temperature. So now, watch carefully. If I increase my temperature, what effect is that going to have on my pressure? Well, think back to the law here. By increasing my pressure, what's going to happen to the temperature? Well, because they're directly proportional, I should say that that also should increase. So therefore, if I'm increasing my temperature in Kelvin, that means I should be increasing my pressure. Okay? Now comes the math part. Got a bug on the screen. Now comes the math part. So when I solve this mathematically, I should get a number that is larger than 410 because I'm predicting an increase. So, here's how we solve it. I go to my table, I find my question mark. There it is. Either above or below that question mark, I'm just going to write that number, 410. I'm going to write 410 millimeters of mercury. So when I do that, I've written that. Now what I'm going to do is I'm going to multiply it by a ratio of my temperatures in Kelvin. And so a ratio just simply mean one number over another number. The question is though, do I want to put 298 over 308 or 308 over 298? Well, let's say you have no idea. Just say. Let's do them both. I'm going to do one calculation where I get 308 Kelvin over 298 Kelvin. And calculate that. I can also do 410 millimeters of mercury, and then I'm going to times it by the opposite of that, which is 298 Kelvin over 308 Kelvin. When I do that, let me get my calculator out here. On the top one, I take 410 times 308 divided by 298. I get a number of 424, and we'll worry about sigmas later, millimeters of mercury, because the kelvins cancel, leaving me with just millimeters of mercury. Then when I do this one, I take 410 times 298 divided by 308. I get a number that is 397 millimeters of mercury. So what's the right answer? Well, both of them can't be right. This is where the ice table comes in mighty handy. If I increase my temperature, I know that's got to increase my pressure because they're directly proportional, correct? So therefore, if I'm starting at 410, I should expect a number that's larger than 410 to be the correct answer. Which one's larger than 410? This one is, making this one invalid. That's not the correct answer. So let's just recap real quick on how I figured that out. I said, okay, that increases, that's got to increase because they're directly proportional. So I'm going to take the 410, the one that's above or below the question mark, 410, I'm going to multiply it by a ratio of the temperatures. Well, notice what I did here. If I want to get a number that's larger, then I'm going to take the larger number over here over the smaller number, not the smaller number over the larger number. If I take the larger number over the smaller number, that should give me a number that is larger than what I started with, which is what I predicted. The final thing that I need to do is represent sig figs. So I've got 2 sig figs here, 2 sig figs here, 2 sig figs there. This guy needs to be in 2 sig figs, which would be 1, 2, round that down, 420 millimeters of mercury. And that is my answer, folks. Okay.